Welcome to another edition of RCE. This is Brock Palen. You can find us online, find all our entire back catalog on rce-cast.com. You'll also find the links to Jeff's wonderful high-performance blog, as well as as well as all of our Twitter handles and everything else like that. I also have, again, Jeff Squyres, one of the authors of OpenMPI, and works for our Cisco systems. So, Jeff, thanks again for your time.
Yes, and apparently I have a wonderful blog that everybody should go read. Actually, there's been some fun stuff recently about process affinity and things like that. I love bringing up that stuff because most people don't appreciate the complexity of the internals of your servers and how it actually affects the performance of your HPC jobs, and you don't even know it. So go read them. They're good stuff.
So let's go ahead and roll right into our guest today. This one's been requested a couple of times, and it's taken a little bit to get this lined up, but we finally have it. We have with us Jeff Darcy of Red Hat, and he's going to be talking to us about Gluster, a distributed parallel file system, but I'll let him get into the details of what's unique about it versus the other offerings and things like that. So, Jeff, take a moment to introduce yourself.
Hi. Good to be here. I've been involved in distributed storage and HPC or semi-HPC for about 20 years since I was working on NFS version 2 back at Encore. My most recent gigs have been working on Lustre at SiCortex, sadly missed, and now I am at Red Hat, where I started a project called Cloud FS, which was based on Gluster FS, and since we acquired the company behind that, I've been one of the architects and, to a large degree, the public face for that project.
Okay, so can you get into a little bit about the details of Gluster?
Well, the idea behind Gluster is that it's scale-out storage. So it is based on the idea of getting a lot of commodity servers. It's largely a cost play. It's a convenience play. It's a little different from some other systems in that it has no single metadata server, and in that it is extremely modular. I sometimes say that it's not so much a file system as a way of building file systems. We just happen to have built one, but you can actually use the interfaces that we provide to build others. So that's actually one of the real key things about it is, particularly in something like an HPC context, where you may have applications that can benefit from a very specific optimization, you can actually build that optimization in because the file system as it is now may not perform that well for you, but with just a little tweak, it can really make a huge difference.
Now, let me zero in on that. What exactly do you mean by an optimization? So this is coming from a guy, I don't know anything about how file systems work. So could you give me an example of, let's say I'm going to be running a specific application and it has a specific file pattern or file access pattern. How does that translate to an optimization that I can build into the file system?
Well, there's a couple of examples that I've come up with. One is the case where this is a little bit far afield, but you have a script that's pulling in dozens of other scripts that are spread across dozens of library directories or something. And the way that things work is to ensure that we're getting current data, we actually have to go look in each of those locations just in case the file showed up there. And so we're actually doing a lot of lookups that fail. And we're not remembering the fact that we did a lookup that failed. So those kinds of operations and those kinds of workloads can perform very poorly. So I actually implemented a translator that remembers the failures. And if we failed within the last minute, then we'll fail again immediately, quickly. That can make a huge difference for those types of applications. Another one, which is probably more relevant, is something kind of like the parallel logging file system that was developed at one of the national labs. And what it does is, as you write out files, it actually writes them locally and then asynchronously will spool them back to the main store later. So if you have a workload that's actually dribbling out little bits of data across a whole bunch of files, if you don't do anything special, that's going to perform really terribly because every one of those tiny writes is going over the network. But with something like this, they all get batched up into huge blobs that get transferred very efficiently. And with PLFS, the real thing, they've seen really significant speed ups on a lot of real applications. And so you can do the same sort of thing in Gluster as a translator.
So that, like, catching everything locally and moving it back, one, don't you have a global file system consistency problem if one of those clients goes away? And two, is this like completely transparent? Is this just like a standard feature, or is this an add-on?
This would be an add-on. In fact, it's one that's still in development, but it's an example of the kind of thing you can do. And yes, you're absolutely right. It's a consistency problem. And what we found with Gluster is that we have defaults that are very strongly biased towards consistency, but a lot of applications don't care about that level of consistency. That they're actually prepared and able to make a small sacrifice in consistency to get a huge performance improvement. So what we've done is, while we set the defaults very conservatively, we've provided a mechanism by which you can relax those defaults in ways that make sense for a particular application.
So, just into that just a little bit more, to do this kind of translator thing, do I have to, as an application writer, and I'm writing my physics application, do I have to use like a Gluster IO library, or when using these translators, can I stick to some sort of generic POSIX open close, MPI file open, MPI file close, things like that?
There's actually a lot of flexibility there. Translators are part of our core infrastructure, which is independent of what access method you're using. So they can run on the client, they can run on the server, they can be arbitrarily reordered relative to one another. So there's a lot of different things you can do there. You can use that core stack through several methods. You can use it through our own native protocol, which uses Fuse on the clients. You can use it through NFS. You can use it through CIFS via Samba. And we do actually have a library API as well. So that's currently being used for our QEMU block storage. So it's bypassing all of the file system stuff, basically. That could be used, in theory, from something like an MPI library, although, as far as I know, nobody's gone down that path yet. So a translator is our name for our plugin interface, which allows you to add functionality or change functionality within the file system. It's actually taken from the GNU Herd project, which is where one of the project founders came from. And the name comes from the fact that it translates an I/O request from the user into one or several I/O requests going down towards storage. But both of those are expressed in the same terms. They're the same API above and below. So that's how we can use those to stack them on top of each other in all sorts of arbitrary and perverse orders and get exactly the functionality that we need for a particular deployment.
All right, so you told us what Gluster is. What is the scope of the project? What are the aims of the project, and who's involved?
Well, the project actually came out of a different background than a lot of other distributed file system projects. It wasn't a PhD thesis. It wasn't an academic or a labs project. It actually came out of a very immediate commercial need. It was a Venezuelan oil company. They needed cheap distributed storage that was better than tape, was actually the performance bar. So it's evolved in a very practical set of directions, very sort of user-focused. And by user, in this case, I mean very generic user, not necessarily a specialist user. So historically, it's been big in areas where they have very friendly, well-behaved kinds of workloads, things like media streaming, content delivery networks, things like that. Now, since Red Hat has picked it up, there's been a lot more interest in using Gluster FS as a substrate for virtualized